Hi, and thanks for joining me once again for another video in which I'm building experiments from this book, Charles Platt's Make Electronics. I'm using the 3rd edition. Now, so far, the book has had us make much use of two fundamental properties of passive components, which is resistance, the ability to resist the flow of electric current, and capacitance, the ability to store an electric charge. And as we've also seen in capacitors, which are the passive components that have that property, they also have the quality of blocking the flow of direct current. Now, in the last couple of experiments, when we've been playing around with coils like this one, we have actually been introduced to a third property of passive components, which is inductance. And the book uses this experiment to give us a bit more insight into some of the properties of inductance. But before we do that, I just want to revisit the use of this coil along with the magnet to generate an electric charge. So let's have a quick look at that first.
So here's my coil and the neodymium magnet that I will use with it to generate an electric current. Now, previously we've used these things, electrolytic capacitors, to store a charge in a battery-powered circuit. So surely the same thing should be possible with the energy that we manufacture with a coil. Well, in theory, yes, but of course what we can't do is directly connect the capacitor to the coil. And that's because this particular capacitor is polarized. So it's expecting current to flow in one particular direction. Now, if you recall, the coil will generate an alternating current and not a direct current. And that means that for half of the cycle, the current will be flowing in the wrong direction for this capacitor. So what can we do about that? Well, there is something we can do, which is to use another component that we've also introduced in earlier experiments, which is this. I know this is quite hard to see, but it is a tiny little signal diode. And if you recall, the property of the diode is that it will only allow current to flow in one direction. At least that is the case for a signal diode like this. We can use the diode to make sure that only the positive half of the cycle being generated is sent to the capacitor. So let me hook that up now and we'll see how it works. From one side of the coil, we go through to the positive side of the capacitor. From there, we come out and into the diode. So that diode, remember, is preventing current from flowing in the wrong direction through the capacitor. And then from the other side of the diode, we go back to the other side of the coil. The other connection that's in play here is just the multimeter connected across both terminals of the capacitor so that we can monitor the accumulation of charge. So let me turn the multimeter on. We've got a very tiny residual voltage there, nothing to speak of. So let me insert the magnet into the coil. And now, if I can do this, hopefully without dislodging any wiring, what you should see is a voltage accumulating there. So we're getting quite a healthy voltage accumulating in the capacitor, which is great. It doesn't look like I'm going to get much above slightly shy of 5 volts there. But that'll do just to demonstrate. Oh, look, now that I've stopped. And then what you will see is that will start to slowly leak away because obviously the multimeter is connected across the capacitor. So that adds a bit of resistance. So the capacitor isn't going to hold that charge infinitely. There will be a little bit of leakage. But you can see we did generate a healthy almost 6 volts there just from the coil. So there you go. So for this experiment, I have yet another coil. And you'll see this, for this coil, I'm back to using ordinary hookup wire, but it's wound tightly around a metal bar. In this case, I'm just using a rod of mild steel. Mild steel is very good for this purpose because it has a high iron content, which means it has excellent ferromagnetic properties, which is exactly what we want when we're using it as the core for an inductor. Now, the book does suggest that if you don't have such a thing lying around, and why would you, then you can use anything of a similar shape and quality. For example, a large screwdriver will do the job. So if we look at the circuit now, where the power comes in, it first goes through a little push to connect switch here. So no power will flow through the circuit until I push that button. It then runs through a little 47 ohm resistor. And at that point, it has two possible paths. It can either go through the coil and then back out to the negative rail, or it can go through an LED here, just an ordinary red LED. Now, of course, current will want to flow through the path of least resistance, and the LED is going to present some resistance. So most current will want to flow through the wires in the coil, which is just conductor. What we should see, you would think, is that in fact when I press the button the LED will not light because there won't be sufficient current passing through the LED to do that, and most current will be passing through the coil. But watch what happens, watch the LED closely when I press the button. Did you see that? It flashed on very briefly and then went off again. So why is that happening?
Now, the mathematical description of what happens in an inductor quickly gets complex, and I'm not even going to attempt to pretend that I understand it. My maths is just not that good, so I'm not going to reproduce it here, but you can look it up if your math skills are up to it. But effectively, what's happening here is that as the current through the coil is increasing, which of course happens when I press the button, it induces a potential difference across the coil with an opposite polarity to the current flow. And that will be seen as a voltage drop across the coil. Now, the energy consumed to overcome that opposing force is effectively being stored as a magnetic field. But once the current through the coil is steady, then so is the magnetic field, and the voltage drop across the coil will be seen to disappear. And this explains why the voltage across the LED was momentarily sufficient to light it, but then dropped away once the current through the inductor was at a steady state. It's parallel to the capacitor, except that a capacitor stores energy as an electric charge and blocks DC once it's fully charged, whereas the inductor initially opposes a change of current, but then allows a current to flow. Correspondingly, while a capacitor will allow AC, an inductor will impede it to a certain extent, and that will be determined by the characteristics of the inductor and the frequency of the AC. And this is something that we'll actually explore further in the next experiment.
So we now have a slightly modified circuit where the connection to the ground rail has been replaced with another 47 ohm resistor, and that is there to provide a little bit of protection for this second LED. Although you won't be able to tell just from looking at the breadboard, trust me when I say this second LED has been wired up so that its polarity is reversed compared to the first LED. So that second LED will only respond to current passing the other way through the circuit. So your instinct might be to say, well, that second LED is never going to light because it's inserted the wrong way round. But now watch both LEDs when I press and then release the button. So pressing, releasing. Did you see that little flash? So that little flash indicated that when I released the button, some current was passing the opposite way through the circuit. Why was that?
So what's happening here is that when current is no longer flowing through the inductor, the magnetic field collapses, and that energy is then returned to the circuit as a current flowing in the opposite direction. And this is what causes the second LED to light momentarily. Again, you can draw a parallel to a capacitor discharging. And this is a property of inductors that you need to take a little care over, because if you're not careful to protect against that reverse polarity flow when the magnetic field collapses, then you can potentially damage other components in your circuit. And in fact, if you recall back to an earlier experiment where we were using a relay, you might remember that we placed a diode across the terminals of the relay. And it was for exactly that reason. It was to protect the rest of the circuit from that current flow when the magnetic field in the coils in the relay collapses. So that's great, because now we have those three passive components under our belt, which is resistors, capacitors, and inductors. And in the next experiment, the book will take us a bit further with our understanding of inductance by using it to build a radio receiver. So please do join me for that.